Hi, everybody. Nice to meet you all. My name is Dimo. I work at Diligence Fuzzing, and we're talking to you today about some work we've been doing with my colleagues, especially with Valentin Wussholz, who is the main designer, on the Scribble specification language. So just to give you a quick plan for the talk, we'll give you a very quick overview of Scribble, answering many of the questions. What is this thing, Scribble? What does it look like, this specification language, one or two examples, and give you just a brief flavor of what's the workflow for Scribble today. Most of the talk is going to be spent talking about the various language features of the spec language. We're talking about how do you annotate functions, how do you talk about contract invariant properties, how do you talk about properties of individual state variables, especially upon update, and several more smaller language features. Talk a bit about future work, like where do we want to take the language, what are directions we think are interesting. For example, how do you talk about the conditions under which a function is allowed to fail? How do you talk about invariants that require reasoning over multiple transactions, especially with respect to ordering of events? There's some good stuff that's already been done out there in this domain. For example, with Verex, and we're trying to adapt what will be most user-friendly from there. And especially one of the big ones, how does Scribble better integrate with other tools, not just the fuzzer? And in conclusion, it'd be really interesting to hear the discussion of what is your use case, what are things that you would find interesting in the language. Right, so what is Scribble? One sentence definition: Scribble is a specification language aimed at Solidity developers. So that is, people that don't necessarily have a lot of verification experience. As usual, it's better to show than tell. So we have a short snippet here from an ERC20 contract, specifically the transfer from function. And the little doc string above it is an excerpt from Scribble snippet. And all Scribble annotations are embedded as doc strings right above the code object that they of whom they specify the behavior. And we hope that this locality, like it's always right next to the thing it's specified, can also help them serve as basically documentation. And it's just a Solidity-like expression, so you can read it almost like as English language. If this function succeeds, the balance of the receiver should be at least amount afterwards. So if you can read Solidity, you can read Scribble. There's one or two extensions on top of base Solidity, but they're not very complex to understand. And so these kind of design decisions hope that they fulfill the goal of making this language friendly to non-experts. Having doc strings is all nice and fun and pretty, but like in the end, you want to check them. So how do you use Scribble? The workflow is that a developer begins by annotating their contracts, and then they run them through the Scribble instrumenter, which confusingly is the same name as the language. And that produces valid Solidity code that should have the same interface as the original code, the same all basic behaviors, except for it has extra checks such that should any of the original notation fails, it will throw an exception or signal in some other way to the surrounding environment that something's not right. And currently, at least in Diligence Fuzzing, the way we use this is running through the Harvey fuzzer, which is a gray box fuzzer that tries to flip branches in a targeted manner to maximize coverage. And seeing as the original annotations, which were comments in the original code, are now actual branches with assert false in the end, these branches become targets for the fuzzer, which is how it actively tries to violate the properties written by the user. So all nice and standard things. This workflow is generic. It doesn't have to be passed down, generic with respect to the backend tool. It doesn't have to be passed just to a fuzzer. So in the past, we've experimented with passing it through the Mitro symbolic execution engine. And we found that for many properties, Mitro is also able to violate them. In many cases, the fuzzer can do a little bit better, especially when it comes to like deeper violations that require, say, 2 transactions or more. But you can also pass it to a different kind of, say, a model checker or a modular verifier. So my colleague Valentin, with some collaborators, I believe, from the University of Waterloo, built a smart ACE verifier which takes Scribble instrumented code and translates it to C, and then uses some standard C tools like CLE and Spacer, I believe, and maybe libfuzzer to either try to prove correctness of some set of invariants or look for violations again. And you can look at their paper for evaluations, but they managed to verify several Scribble instrumented properties. We've done some small experiments internally with SMT checker, which I think now is called CMC. And I was able to deal with small function-only invariants inside of a single function, but I think if I remember correctly, I still had trouble with the encoding of contract invariants. So we'll talk more about this in the future work section, but this is an area we're actively interested in, making instrumentation friendly enough to a variety of bytecode-based tools. And this is the second goal, I guess, partially of the language, but more of our workflow at the moment, to make sure that it's agnostic to a variety of bytecode-based backend engines, whether that be fuzzers or some other animal. So this is basically just a quick flavor of Scribble and how do we use it today. So let's just drill in the various language features, try to provide enough examples, and talk a bit about instrumentation as well. So we've already seen the first type of annotation, function annotations. They're all prefixed with the if succeed keyword, and from the keyword you can guess the semantics. If succeeds, P checks that P holds upon successful termination of the function. So P is equivalent to a post condition. Currently P can be any pure valid solidity expression, Boolean solidity expression. Now we use the term pure here in the sense, the traditional sense that it doesn't change state. You can call view functions if you'd like here on this or any contract. And this current example, the annotation is kind of unsatisfactory. After transfer form, we should be able to say something more than just that the balance of the receiver is a case amount. We want to talk about by how much does the balance of the receiver increase. And to do so, you need to start talking not just about the state of the contract after the call, but also before the call. And you can use this with the traditionally named old keyword that allows you to refer to the state of any expression before the call. And this is basically what you need to do to specify that the balance increases by amount. You can use old now to encode traditional pre and post conditions. The traditional HOR triple PSQ can now be encoded as if succeeds, old of P implies Q. And obviously implication is just syntactic sugar that Scribble adds. Currently, we only allow primitive value types inside of old, but that's just an arbitrary restriction that we chose to make sure that the instrumentations that are generated in practice are not too heavyweight and don't copy dynamically sized data structures, but it's basically a matter of flip of the switch to allow looking at the old values of arrays and structs as well. How does that annotation what does it look like when you compile that instrumentation down to solidity? So something like this would get generated here, and we'll step through the various parts of this because it's kind of ugly looking, I guess. So we inserted a wrapper to interpose on the execution of transfer from with the same name and signature. The original function is just renamed, moved to the side, and made private. And it's invoked in the middle of the wrapper. And the compilation is exactly as you'd expect. The value of old is stored before the original call, and the check is your standard, if not condition true, assert false. Perhaps the only weird thing is what's this vars thing here? Like, why don't you just use temporaries? So in early experiments, we found that compilation can create a bunch of temporaries, which could lead to stack size problems for the solidity compiler. So to avoid those, for now, we're bunching all the temporaries inside of a single memory struct. Logical question you may ask here is like, why are you wrapping a function in a function when Solidity gives you perfectly good mechanism to do this? It's called modifiers. Turns out that it actually varies, so I believe from MSR used verifiers to achieve this goal. But turns out that in a modifier, it's tricky to access the return value of the function. So to gain that little bit of extra expressivity, we've opted in for instrumentation with function interposition. So that's function annotations. So what happens when you want to talk about invariants over the entire contract state that are maintained through the lifetime of the contract? You can specify it with the synonymously named invariant keyword, again, as a docstring right above the contract. So in this example, we have a dummy ERC20 contract and has the mapping balances and a total supply state variable. And we basically want to state what we'd expect to be true for a well-written ERC20 contract, that the sum of all balances is always equal to the total supply. So the semantics of these invariants is what you'd expect. It's a predicate over the contract state that holds at all observable points. We define an observable point as any point in which control flow is outside of the contract. So you expect the invariant to be maintained before you enter the contract, and you expect the invariant to be reestablished before you exit the contract. And obviously, the reason we do this is that, as you all know, invariants can be temporarily broken while the contract is updating its own state. For example, in this case, in the transfer from function, you squint a little bit right between these two lines when you've updated the balance of the sender, but before you updated the balance of the receiver, the invariant is violated. And again, this is similar to the standard object invariance in literature, I believe in JML and Spec Sharp. So how do you instrument these contract invariants? What does the code look like? Well, there's three places where you need to understandably insert checks. First of all, you need to establish that the constructor, at the end of the constructor, the invariant is established at the beginning of the lifetime of an instance of the contract. Next, you need to check that whenever the contract returns from an external call, it reestablishes the invariant. So that's in the end of all public and external call functions, you need to check invariants. Now, obviously, there's a little bit more details in the case of public functions, which can be called internally, but that's just handled with a little bit of extra code. And finally, before the contract makes a call out to another external call out to another function, you need to make sure that it reestablishes its own invariants. These three categories of checks can be used together to check the inductiveness of the invariant. Right, so now we've talked about how we can talk about the behavior of individual function and invariants on contract state across multiple transactions. Another type of invariant we found useful in practice is talking about what happens when you update a single variable. So for example, say we have an owner contract, those usually have an owner private variable. And what you'd expect from usually from an ownable contract is that only the current owner can transfer ownership to somebody else. And one way to express this is by saying that should the owner variable be updated, it must be the case that the current sender is the current owner. And this is what this annotation basically specifies. Note the use of old here. Old refers to state before the update of the variable, as you might expect. So the old owner. As mentioned earlier, these are predicates checked every time a state variable is updated. If this is a complex state variable like array or so on, it's checked every time the whole variable is reassigned or some part of the variable itself is updated. So as in this example, we find that this is often useful for checking permissions on various parts of the state of the contract. You can also use it to check more fine-grained data structure invariants, stuff that you don't want to hold just at the contract boundaries, but also on every single assignment, every update in the middle of the contract. For example, you might want to say that the owner is never the zero contract. Right. So same question, how do you instrument these? What does the code look like? As you can expect, first you need to identify all AST nodes where updates may happen to this variable, which usually mainly is just assignments, but there's several other kinds of nodes, delete nodes. For array types, there's like push and pop node, like function calls to the built-in push and pop functions. I think there's one or two more cases here. All of these sites are expressions, and they need to be interposed and replaced with expressions themselves. So we do this by generating wrapper functions for each of the updates and replacing the AST node with a function call and compiling all the annotations inside the wrapper. So again, in here, here's the original assignment that's being moved into the wrapper, and the rest of the code around is just implementation that checks the if updated. So store the old value of the owner, and then after this update, check that the owner is not the old owner is this message sender. Now, again, I mentioned this is an assignment and this is an expression. Unfortunately, in Solidity, assignments are expressions that can be nested arbitrarily inside of other expressions in the tree. So we do need to also return the newly assigned value here. Now, obviously, you're asking, like, what about aliasing? It's too good to be true to do this just on ASTs. So to motivate the example, if you have an address, an array of addresses, say admins, and you want to check that the zero admin is not the first admin, is not the zero address. Now, if admin is aliased by a storage pointer, you can obviously update the first admin through that storage pointer, and seeing if storage pointers can be passed around arbitrarily. It's undecidable in general and very difficult in practice to find all locations where a particular array, maybe a particular state variable may be modified through a storage pointer. So for now, we reject annotations on potentially alias variables, where the detection whether a variable is alias is kind of done using a very conservative AST-based check, basically looking for any assignments where, including implicit assignments to function arguments, where a state variable or a part of it may leak to a storage pointer. We're currently working on removing that annotation by simply adding runtime aliasing checks to our instrumentation, so basically to avoid this issue altogether. Right, so this annotation is written like this dummy annotation, for example, is actually kind of, again, ugly, right? If you don't just want to say that the first admin is not the zero address, you usually want to say that no admin is the zero address. And to do so, you need universal quantification, which is now supported in Scribble. So if you want to say that none of the admins is the zero address, you can express this using the following for row annotations. Row annotation, whenever admin is updated, for every index I inside of the admin array, it's true that the ith admin is not the zero address. And as you can expect, instrumenting a for row quantifier introduces a loop somewhere in the checks. So we caution people to use universal quantifiers for now carefully. Like when you can get away without using universal quantifier, it's always better, because obviously introducing extra loops makes the problem of state space and path explosion problematic for tools other than the fuzzer. So the fuzzer can kind of shrug it off and just keep chugging because it's all concrete values. Though even in the fuzzer case, we've observed some cases where clients have had way too many for rows, and the end result for that is longer execution time per test case and fewer test cases per second, resulting in a slower reach of to satisfactory coverage for the client. So even in a fuzzer case, it's always better if there's another way to express a particular invariant that doesn't require to add loops in the instrumented code. And we haven't done yet many experiments with universal quantification in Scribble and how other tools handle it. And this is actually a very interesting topic for us to move on forward. Right. So universal quantification is also supported for maps, not just array containers. So for example, if you have some token where the owner of the token is not allowed to hold value of this token, you can express that by doing an if updated annotation of the balances array, saying that for any address A in balances, either A is not the owner or the balance of A is 0. Now, the obvious question here you're asking is, well, by definition in the language, maps are defined over all possible keys. So there's 2 to the 160 keys here. And obviously, we can't iterate over that much values as part of a runtime check. So the way we've defined for all over maps is it's an iteration only over the explicitly assigned keys. That is, keys that have been assigned keys once, and they have not been deleted through an explicit delete of AST node operation. To implement this, maps have to be rewritten to keep track of all the keys that have been explicitly assigned. And as a result, because you have to also rewrite all locations where a map is assigned, we also don't support map quantification on alias variables. However, that is going to be removed soon as well. That restriction is part of the ongoing work. So map instrumentation can be a little heavy. That's, I guess, the one warning thing for it. So what does that look like? Let's say that the balances map is mutated somewhere in the code. First, we rewrite. Actually, the zeroth step is that we generate a specific map data structure for this particular map type. The first step is that then we rewrite the map to our custom data structure. This is all generated on the fly by Scribble. Next, we also rewrite all map updates. So first, this line gets written because of the if updated annotation. And then even the original moved assignment inside of the wrapper gets written to a call to the specific library function for that particular library type, the library from addresses to unit 256. And there we keep track of the keys as expected. Currently, as part of the set big effort on adding runtime aliasing checks, we're also going to be working on removing parts of this instrumentation, specifically the part where we rewrite a map into a struct. And this is going to keep the code, the instrumented code, quite a bit cleaner and closer to the original code. Another related feature to maps, to sort of rows, is the sum aggregator, which you've actually already seen in an earlier example. So as you can guess, unchecked sum computes the sum, the unchecked sum of any numeric container, whether it's a map or an array. Currently, only one-dimensional containers are supported. We will be interested to see if there's demand for more higher dimensional numeric containers, but for now, there doesn't seem to be much. Array sums over arrays are currently instrumented as loops, the boring way. However, when we talk about maps, there are actually no loops inserted for this instrumentation. Specifically because we already do this heavyweight rewriting for maps, it's easier for us to also add a ghost variable that keeps track of the current sum for the map. And seeing as maps cannot be in Scribble, in Solidity, reassigned as an entire container with the expensive copy operation, it's actually no need for ever to run an actual loop to compute the sum of the elements of a map, because it's always basically a one element change per operation. So that's all nice, that there's no extra loops, heavyweight loops inserted for map instrumentation. And we're actually, as part of that ongoing big work effort, we're working on reducing the loops for array sums. And so the way you can do that is by keeping references from, keeping a map from essentially the pointer for a particular storage array to its currently held sum. And there's still some cases where you're going to need loops, basically when you reassign an entire array to a storage pointer, because there's obviously a whole copy happening where in a single AST operation, multiple values of the original storage array are being modified. But in all other instances where you're just modifying a single index of a storage array, even potentially to a pointer, you can still only do a single update to the ghost sum. Right, so that summarization is one of the more heavily requested features, And the last type of annotations I want to just mention today is inline annotations. And I guess this is the last example for today, just going to motivate them with a batch transfer function. So we have in this batch transfer function some token, a sender, an array of receivers, an array of amounts that each receiver should get, and the bodies as you expect, a simple loop. And let's say that we want to specify that we expect that all transfers should succeed. You could try and implement this first as an if succeeds annotation with for all, like saying that for each of the receivers, we expect that their balance should increase by the respective amount. And this kind of looks okay, but if you try to run this through the fuzzer, it will actually quickly violate it. And the case where this actually doesn't hold true is if receiver has duplicates. This invariant is actually not true in that case. Also, even if you have additional annotations that specify the receiver does not have duplicates, it's still the case that we add extra loops. And we're working hard to basically reduce the number of loops in instrumentation with an eye forward to working with tools that most traditional static tools, they frown a little bit at loops, like they require extra work. So can we do this in a different manner? And in this particular case, we can actually do this by adding inline inside the function body let and assert statements that let us talk about just each individual transfer. So this is how that would look today in Scribble. You can also, so the first annotation basically is kind of like a ghost temporary local that's just being bound here, old balance, which stores the balance of the receiver, the ith receiver before the transfer. And the assert below is equivalent to a normal solidity assert, but you can also use any ghost temporaries that are in scope at the moment, like the old balance one. And the 0 in the bottom is a hack due to a limitation in the Solidity compiler AST generation, which we'll be again removing in the next 2-3 weeks, hopefully. So this kind of gets around us not having to do a loop. But on the other hand, it adds inline annotations. And if you try to keep a specification pure and kind of separate from the implementation, this is obviously not a very pretty annotation. So it's there when you need it. It's kind of an escape hatch. It's there when, for example, the annotations at the contract or the function level are not expressive enough to get to what, say, a client wants. But on the other hand, if you want to be pure about it and just keep the specification only over the interface of a contract and not over its implementation, then this is obviously a little bit less desirable. Yeah, and also useful to sometimes reduce the number of universal quantifiers you may use in annotation if you find that your instrumentation is getting heavyweight enough that it's getting in the way of getting your job done. So these are actually all the language features I wanted to cover today. And I wanted to mention briefly a couple of items of future work. So first thing that we've actually been getting quite a few requests from clients is being able to say something about what are the conditions under which a function is allowed to fail. Right? So one thing we've been playing around with is the idea of an if aborts annotation for external functions. Like, say, for example, we expect this dummy div function should only ever fail when the divisor is 0. Now, obviously, any function can fail due to gas exhaustion, so the instrumentation model would have to account for that. And the semantics of the function basically accounts, the semantic of the if aborts annotation is that it should cover all non-gas related failure conditions. So part of the reason why we haven't gone ahead with this is that there's a bit of a lack of regularness. It's because of the semantics of DVM, where you can only catch exceptions at an external call site. Supporting this for non-external functions gets a little bit tricky, especially say for public functions, which can be called internally and externally. So we're still trying to figure out a good way of doing it. We've also been playing around with the idea of there are ways to do this that are specific to our tool, but we don't want to do that yet. We want to see if we can come up with something a bit more agnostic again to the backend tooling, to the whatever you're using to check these annotations. Another piece of future work that is very interesting is invariance over multiple transactions, reasoning about ordering of events. And now the big thing in literature here is, Verex has already has a tool that's been using past LTL to express and check these invariants. And we think that's I think it's a very neat and clean way of expressing it. Though we haven't gone with that direction quite yet, because one of the major goals for Scribble is to be friendly to non-verification experts. And LTL annotation sometimes can be a little surprising or confusing for non-experts. Alternatively, we'll be looking at using some form of ghost state that's a bit more unrestricted, but that obviously has its own set of issues. It's not as declarative and succinct as an LTL annotation would be. So that's still spec'd out, and we're open to any feedback from the community and ideas for how you might want to support this. In terms of a bit more implementation, we're trying to make Scribble more modular. It's currently this giant blob of a tool, an NPM package, but it can be separated into just the front end, which has the Scribble AST parser and type checker, and the rest of the machinery, which is instrumentation. And by doing this, we hope to enable people to build easier tools on top of Scribble. Like if you just have the front end, you can easily build, say, a translation tool from Scribble to a different spec language, or you could try and build an alternative implementation that compiles Scribble down to expressions over EVM bytecode state given stack maps, which would be which basically allows you to completely sidestep the need to instrument. So that'll be kind of cool. So that's coming down the pipeline soon too. And finally, I think the most important one is exploring integrations with other tools. So far we've done some experiments with SMT Checker and with Smart Ace, but there's a lot to be desired there. And specifically, the questions there is either how do you communicate out of bound to set tool that say this is an invariant, this is a notation, like treat this part of the code as something that should be trusted by verify. Or how do you make the instrumentation more friendly? And it's that same vein of thought, we'd love to see like how friendly Scribble instrumented code to the Certora prover, and would love to collaborate with anybody that's interested in this. And we're very open to learning what are the things that we can do better when we generate instrumented code, or what are the alternative ways to integrate. In conclusion, talked a bit today about the Scribble specification language. Main goal for the language is try and be friendly to Solidity developers, normal humans way out there, trying to just write their code. And talked a bit about how we instrument in our workflow, and we're hoping to try and keep it as agnostic to the backend tool as possible. Yeah. And with this, please check us out on GitHub. We welcome pull requests, issues, whatever you have. Reach me at my email. And thank you. I would love to hear your questions now.
Thank you. So one kind of I don't know how much you have seen our language, the CVL. It sounds like in the CVL we model the EVM, and we model the environment of the EVM. You probably have similar things here, or do you?
Can you define what you mean by model the EVM? Can you give me an example, just so I get an idea?
I'm not very technical. The teams are probably more technical, but I guess in Solidity you have the message sender, but we are having a lot of other things that you, maybe somebody in the team can help me, but for example, yeah.
So there is a lot of stuff sent along with the call, right, implicitly. So
like block timestamp, block Coinbase, yeah. So anything that's exposed by the ABI at the Solidity level is available to us, right? So the ABI exposes, like, there's several structs here. There's message dot, and then various things: message dot data, message dot value, message dot gas, blah blah blah. And there's the block built-in data structure, which is block dot timestamp, block dot Coinbase, block dot difficulty, number, and so on. So basically, anything that's available at the Scribble at the Solidity level is, yeah, available here as well.
Okay, so I was wondering if Muli is done with this question. Like, how are your experiences with the backends? So I understand you're mostly using fuzzers, or also something. Okay.
Fuzzer is the main case. So basically, everything else is at the experimental level here. Smart Ace is basically the most fleshed out experiment. There's a VMKI paper on it that you can kind of see, so you can see the kind of invariants that have been pushed away through. And as mentioned earlier, Smart Ace is basically Solidity translated to C, and then using libfuzzer, CLI, and spacer. So CLI and spacer try to actually prove, especially spacer actually proves absence of violations. Libfuzzer obviously tries to find any violation. And CLI, being concurrent execution, also just looks for violations intelligently. Doesn't prove absence.
I can say a bit more. I am one of the authors of the Smart Ace, actually.
Oh, please.
So basically, what we did at that time, the main thing was to use the model checker. So it's true what he said, Dimo, right? That basically we also use CLI and libfuzzer in the experiments, but the main thing was to use the model checker. So in that sense, I think it was similar to what we do with CVT and CVL, but it was at the Solidity level, right? So the specification at that time, they were easier to write, probably.
Yeah. And
it was also following what also Dimo mentioned, right? This paper from from Martin Bechev, right? The Beriex, or how it's called, yeah.
Verex, yeah.
Verex.
Yeah, well, basically they already wrote all the specifications. So basically what we did is, at least for some of the experiments, basically was to copy the specifications they wrote. But I remember also we wrote our own specifications for some real smart contracts. So.
Yeah. And so I don't know if you share this experience. To continue answering your question, I did a couple experiments with SMT Checker, and what I found with SMT Checker at least was that the place where it kind of started struggling is when it tried to discharge contract invariants. So, you know, for those, and at the time it wasn't clear if the problem was with the Scribble instrumentation. It was encoding these invariants in a way that wasn't obvious that these are contract invariants to the SMT Checker, or the issue was with SMT Checker as well itself, which was, you know, it's still kind of, I don't know if they call it alpha or beta, but it was still kind of earlier on in its development. So that's, I think, the good benchmark to try, because single function if succeeds annotations are relatively easy, usually, unless there's loops in the function. But it's the contract invariance that is something that should work if we did our job right. And in my earlier experiments, there was still some issue in communicating those. So that's what I would start, at least. I don't know. I'm sorry. Was it Jorge that was in the paper?
Yeah.
I don't know if you have any experience with spacer and contract invariance.
I think we had some of them. I remember actually for all the specification, what we didn't use because we really try hard is not to use quantifiers, right? So, and we didn't need to actually for most of the properties or for all the properties. So yeah, that was basically the main thing I remember, right?
Yeah. I hope that answers your question.
Yeah, I was just curious, yeah, in general. Thanks.
I have a question on the fuzzer. So does it start from the constructor and do step by step, or does it start with like arbitrary states and execute one external function?
Oh, so you're saying does it start from an empty state and instantiate a contractor from a specific state and then continue from there on?
Yeah.
Okay, it starts from, you can both. You can basically specify what the starting state is. You can start from an empty state, but usually in practice, what we do is we start from at least in it, like, especially when we do a client work, like we start from a fully deployed state of a system of contracts, because usually that's what people care to look from. So in practice, usually we start from a deployed state, but it can deploy contracts, and it does try to deploy contracts as well, I believe. Actually, I'm not sure on that. I need to ask Valentin. But
maybe following on Nurit's question, the idea is the user has to stay with what state it does. It's not actually, it's not formally verifying anything. It's just user, it's a simulate this from a state that you know.
Yes, it's yeah. I mean, it's a fuzzer, so by definition, it's not able to formally verify anything.
So it's a
state generation.
So it's a fuzzer on the arguments, but not on the state. The randomness of the fuzzer is on the arguments to them.
It does fuzz some of the state. It will fuzz block numbers and block timestamps.
Okay.
I think there are a couple of other environmental parts of the state that it will fuzz, but you're right that it will not fuzz the storage of a particular contract. That's all concrete.
Yeah, got it. You got it. Yeah, because yeah, that's like one serious case of false negatives when you start with arbitrary states.
Yeah. It's not, the state is not simple. There's the only thing, it's not symbolic. Yeah.
And following on from that, when you're doing the fuzzing, are you executing a single method, or are you executing a series of transactions starting from that state?
A series of transactions. Now,
okay.
Yeah, a series of transactions. Given that we're fuzzing the block number, you can also group multiple transactions in a single block, right? Because the fuzzer has a choice whether to increment or not the block number for consecutive transactions. Sorry, let me not call it transactions, for consecutive message function calls, root external function calls.
I had a question about your specs are written in the contract implementations, it seems like. Do you have any support, or have you thought about reusing specifications for multiple contracts that implement a similar interface?
It's a great question. So we have a macro implementation exactly that does exactly what you say. Like you can specify a macro, say for like anything that looks like an ERC20, I want you to add all these annotations on these particular functions with these signatures and on these variables. Yep, it's there. Honestly, it's not the cleanest design. I don't like it, but other people like it. So there's YAML-based macros. It's somewhere in the documentation. Yeah.
And I was also wondering if you had support for, so in your function annotations, you can say if the function succeeds, it has the following effects. Can you also say that it doesn't have other side effects or put limits on sort of what things it can touch or what things it has to keep the same?
So like kind of like the modified list in like Boogie, like
yeah.
List exactly the set of modified things. No, not really. You could say stuff like the value of something specific is the same as before, but that's not what you're asking.
Right.
That's not the same as whether it's modified. So no.
Yeah. Okay.
On the implementation, somebody else has a question.
Thanks. One question. Is it only meant to be used on static code, or do you also use it for, I don't know, for detecting violation on dynamic environments? On
Can you
runtime?
define, can you explain dynamic environments here? I don't think I quite understood the question.
Well, I can think of ways to use fuzzing for during actual runtime execution, like integrate with an Ethereum node and fetch the current state and trying to see.
You mean like with the live main network, not just with our own states?
Yeah.
Right, that's a very good question. Actually, we currently have somebody doing their master thesis with us for the last couple of months who's actually exploring exactly that in a slightly different one. Not through the fuzzer, but actually by trying to build a separate tool that takes Scribble annotations from a particular contract and then looks for violations on mainnet for deployed instances of that contract. So we have that going. I believe Harvey can start from an arbitrary state. So Harvey can also start from pick some block from mainnet and start from there fuzz particular contract. So that's also possible. We haven't done that though with the fuzzer. We're doing it without the fuzzer just by like trying to look for violations of a particular property on mainnet. Does that answer your question? So technically, yes, it's doable with the fuzzer. We haven't done that. We're doing this without the fuzzer, kind of experimenting right now as well. Kind of runtime monitoring is what I think you're suggesting of mainnet.
So another question is that you are integrating with engines which are academic. Is there a reason why you don't integrate with industrial tools, open source like Slither or Manticore? Is it not interesting or hard, or sounds like you only integrate with academic work? Is it because it's more interesting, or because from our customer, it's just like Slither and Kidna and Manticore, this is what they use industrially as open source tool in addition to Certora. Right.
So Slither itself is more of a traditional static analyzer, so it doesn't really kind of. I don't think it fits the use case very well. Echidna does. Echidna is a fuzzer, so it can actually look for these violations. I think basically for us it's a lack of time and man hours to actually integrate all these tools. So we just picked one and went with it. So I think Valentin is running Echidna separately as part of his benchmarks for Harvey. I don't know if he's running it with Scribble properties, so I'm not sure if that's been looked at. Slither, I think, doesn't quite fit the bill because of the type of tool it is. Like Slither will not be able to create a counterexample to show unless they've changed it a lot since last time I looked at it. Cannot generate say counterexamples and show you test cases why a particular violation assertion fails. It's more like a traditional data flow analysis and certain set of static analyses. Somebody correct me if I'm wrong here. There are potentially other industry provers that we have not looked at definitely. And the reason is not that they're less interesting, it's just lack of time. This is the first ones that we picked up and run with them. And the reason, for example, why we chose, say, SMT checkers, because it comes from the Solidity team and is maintained within the compiler. So we're hoping that it has a higher chance of surviving long term because it's not part of the compiler. So we're also kind of trying to pick tools like that. But honestly, if there's a tool we haven't tried, it's just because we haven't had time yet.
Thank you.
I have one question. Do you have anything to say about on average, how many lines of annotation people are writing in Scribble for, medium-sized contracts?
That's a great question, and I don't have an answer to that. It's a great question. I have not looked it up, but thank you for pointing it out. I should look it up.
Thanks.
Well, perhaps you know how long it takes to write to write a spec for a new contract.
Depends on who you ask. So I can give you a couple anecdotal examples to transfer the questions, which are far off from a full answer to what you're looking for. I've tried to write in some engagement. I've tried to write specs myself for client code, and it takes a long time. It's taken me, like, say, for a code base of several thousand lines, it's taken me, say, 2 weeks to come up with 10 or 15 good annotations. But most of the time is actually spent me trying to just understand what the hell the code does. So now, if you have a developer that knows what the hell is going on, for them it's the inverse problem. It's trying to understand first the language, which usually takes about a day, and it's not really understanding the language, it's getting used to how to write things, how to express themselves in that language. The language is simple enough to understand. It's like 5 or 10 constructs on top of Solidity. It's learning the idiomatics of the language, and then it's learning to avoid the pitfalls. And so after this 1 day kind of learning curve, it's however long it takes them basically to wrestle with the fuzzer. Because what usually happens is they write a bunch of invariants, the invariants are violated, they look at the invariants again and say, oh, I actually had the wrong understanding. I didn't think about this and this in this case. And it's this iterative process where they refine their invariants over the set, say, on average, say 2 weeks, until they get to something that where the invariants, the fuzzer can no longer violate the invariants. Or they fixed all either the invariant issues or code issues that they found in that process. And how many invariants they'll write in the 2 week process, I don't have a good estimate here. It's usually somewhere in the double digits, but how much, I can't tell you. It's a good question though, to have that stat ready.
How long in terms of runtime does it take? I haven't used a fuzzer before. Does it take minutes, hours? I mean, I guess with a fuzzer, you can keep running and generating examples as long as you want, but exactly. in practice, like how long does it take to find violations or to get confidence that there aren't any? So
those are two very good questions. The first question, how long does it take to violations? Again, wildly depends on the code base you input. In practice, I've run basically 24 to 48 hour campaigns. In the beginning, when you first write a couple annotations to start, you usually get violations pretty quickly. Like you get a violation within like 10 to 15 minutes. Those are because usually there's simple cases you missed that are easy for the fuzzer to catch. And then getting violations becomes trickier and can take say up to an hour, 2 or 3. In my own experience, usually if the fuzzer can make it past 4 or 5 hours without finding violations, it gets to be relatively unlikely that it'll find something in the end. Now, gaining confidence itself is tricky because it's trying to basically answer the question, answering the question, what's the probability that you'll find that there's a violation left if you keep running for X more amount of time, is fundamentally an undecidable question, unanswerable. So I think, Valentin, you have to look at the Harvey paper for details, but he uses a proxy for that estimate. Basically, the proxy is it's some estimate of the probability that given the number of new branches flipped in the time that it's been running so far, what is the probability, assuming some form of regularity here, that with X more amount of time, we'll find a new branch to flip. There's some assumption there about the regularity of the code that's formally specified somewhere. I don't know it because I didn't write that. And that gives you this kind of confidence score that no new paths will be discovered should you keep running. And that's the proxy that is being reported by the hierarchy fuzzer to users, like this kind of estimate of probability that new paths will be discovered. So that's kind of trying to answer the question you're saying, like what's the point of running the fuzzer for longer? But I don't have a lot of details there more than that.
Yeah, but in practice, you said people will, at the beginning, get violations.
Yeah.
Yeah. Okay. Yeah.
But on practice, people like campaigns that I've seen 24 to 48 hours, multi-core. So like it's actually like, all right, because it's cumulative in terms of CPU hours. It's maybe closer to like a week of CPU hours, but it's
sure. Yeah.
Wall clock time, 24 to 48.
Thank you.
Though I could also be like a bit off because like I haven't been like looking at the campaign stats in a while. This is as of 3 or 4 months ago.
Are you interested in supporting other front ends?
What do you mean by front end?
Sorry, like other languages, not Solidity, but maybe other smart contract languages.
Yes, that would be amazing. I think though, I don't know if we have the manpower right now to implement on ourselves, on our own, like another language. But again, part of this is like a call to please. We're very open to collaborating with people and opening up as much as we can. So yes, we're very interested. I don't think we have the capacity right now to implement, say, Viper would be the obvious next one, but it would be wonderful, yes. Like, I think implementing Scribble, so there's also a little bit of a problem there, right? Because by definition, the idea of Scribble is it should be the same language as the underlying language, so it's easy for developers. So if we're trying to do Scribble for Viper, we would basically probably, one way that we could do this is by using the Viper syntax, and that's basically building a whole new Scribble dash Viper. And it's essentially re-implementing everything from scratch. Not everything, but a lot of things from scratch, right? Both the AST, the parser, the type checker map, the type checker even are going to have to be Viper specific in the instrumentation too. That'd be cool, yeah, definitely. But it might become its own thing. Like having a single spec language that's the same for both Solidity and Viper, I think might not be the same design goal as Scribble, which is, be friendly for the developer community of that particular language.
Right.
But what ideas though, if you have ideas and suggestions how to do it?
Cool, thanks.
How is Hawaii?
Hawaii is beautiful. We're about to get a swell tomorrow that I'm very excited for. If you guys want to see, I can actually show you the view.
Yeah.
But I need to first disable.
Are you a surfer or what?
I was not a surfer, but then I moved here, and it's hard not to.
Muli, are you thinking about opening an office in
Hawaii?
Hawaii?
It's a state, no? Is it a state or am I wrong?
It's a state. It's a
yeah,
state.
well, so
maybe
we are. Yeah.
Maybe you should do a workshop in Hawaii. Come visit.
Sure.
Yeah, let's do a company retreat.
Exactly. Yeah.
I agree.
Okay, more questions on the team from the. Yeah, no. Oh, thank you very much, Dimitar. Navid, you're good.
Yeah,
Thank you very much for the questions, everybody.
Yeah.
It was a very interesting discussion. Thank you all. Please feel free to reach out. We're open to ideas, discussion, collaboration all the time.